Hey guys, it's Austin Chen, and welcome back to another video on the 2020 AMC 12A. Today we'll be working through problems 6 through 10. We're changing the editing a bit, in that the problems will now pop up in the beginning and end instead of staying on screen, so that the whiteboard can take up more of the screen. You can also pull up the problems on your own by a link in the description. Let us know if you have any comments on this change. Alright, so let's go ahead and get started. So we have number 6. In the plane figure shown below, 3 of the unit squares have been shaded. What is the least number of additional unit squares that must be shaded so that the resulting figures has 2 lines of symmetry? Alright, so what we should do before trying to solve this problem is find any possible lines of symmetry of the following figure, because at the end we want the figure to have 2 lines of symmetry, and we should find the lines of symmetry that are possible, so then we can consider which are the best to use. So I'm going to go ahead and draw our figure right here. So it looks like we have a 5x4 rectangle. So it's going to look something like this. And so let's go ahead and just find the possible lines of symmetry that it could have. And so we have a horizontal line of symmetry, and we have a vertical line of symmetry that goes through the middle column of squares because there's an odd number of columns. And now, are there any more lines of symmetry? You might think that the diagonal of the rectangle is a line of symmetry, and it looks pretty good, right? It looks possible that if you flip this section over to this section, that it would be symmetrical, but it's actually not. So if you have any kind of rectangle that is not a square, the diagonals are never lines of symmetry. And you know, it may look congruent to this side, but if you flip it over, it actually overlaps over a different area than this triangle right here. So the diagonal is not a line of symmetry unless our rectangle was a square. So what does this tell us? This tells us that the only lines of symmetry is this vertical line and this horizontal line. And guess what? The problem wants us to find the problem wants us to shade squares until we have 2 lines of symmetry. Well, there are only 2 possible lines of symmetry. That means our figure has to have these 2 lines of symmetry, and that makes the problem a lot easier. So we'll go ahead and work out the problem, knowing that those 2 lines of symmetry are the ones that we have to have. So I'll draw the figure again, and I'll shade in the boxes that they've already shaded in, which is this one, and this one. And I'll draw the lines of symmetry that we need to have in our figure. So it's telling us that we have to shade more unit squares until we have that this figure has these 2 lines of symmetry, and we want to shade in the least number of additional unit squares. So let's figure out which squares we have to shade in first, and see if there are any squares that may be like somehow like optional, like you might have it or not, but you know, we'll see what happens. So let's look at this horizontal line of symmetry first. If this line is going to be a line of symmetry, that means this square has to be shaded from this square, because this square will reflect over to this square. Actually, I'll mark the squares that we shade with an X, so it will be easier to count which squares we shaded at the end. So I'm gonna have to shade in this square because of this square over the horizontal. I'm gonna have to shade in this square, likewise over the horizontal, and this square as well from this square over the horizontal. And now we'll consider the vertical line of symmetry. From the vertical line of symmetry, I'll have to shade in this square from this square. It will reflect over here, and this square will reflect to the end right here. And this square is already in the middle, so it won't reflect to anything. It's same with this square. But this one will reflect here, this one will reflect to here. And now we've shaded all the squares that we had to shade in, and there are no other squares that we have to shade in because, it's already symmetrical, and we don't want to shade it anymore because we only want to shade in the least number of squares. So let's just count the x's that we shaded in. 1, 2, 3, 4, 5, 6, 7. So there we go, we shaded in 7 squares, and we have to shade in those squares, and that's our answer, D7. So let's move on to number 7. 7 cubes whose volumes are 1, 8, 27, 64, 125, 216, and 343 cubic units are stacked vertically to form a tower, in which the volumes of the cubes decrease from the bottom to top. Okay, that already sounds like a lot. Let's just work with that line so far and see what we have. So we have 7 cubes, and we're given the volumes of those cubes. They're stacked vertically to form a tower, and the volumes of the cubes decrease from bottom to top. So the bottom will have the largest volume, and the smallest volumes will be at the very top. So it'll look kind of like a pyramid shape, but with cubes stacked on top of each other. You may notice that the volumes are actually all perfect cubes, which means that the sides of all the cubes will be integer side lengths. And actually, these side lengths are consecutive starting from 1, because we see that our volumes are, 1, 8, 27, 64, and so on. And this is just 1 cube, 2 cube, 3 cube, and so on. And to 7 cube, because we have 7 cubes. So basically, this is telling us that all of our cubes are going to be side lengths from 1, 2, 3 all the way to 7, them being integers. And so let's go ahead and draw the tower. So it's going to be the largest volume cube on the very bottom. So that's going to be our side length of 7 cube, and then we'll have our side length of 6 cubes stacked on top, and then it'll get smaller and smaller as we go up. And then the tower's really long, so I'm not going to draw all of it. I'll just draw a dot dot dot, and then I'll put the very smallest cube at the very top with a side length of 1. And now let's read the rest of the problem and see what we have to solve. Except for the bottom cube, the bottom face of each cube lies completely on top of the cube below it. What is the total surface area of the tower, including the bottom in square units? Okay, so it wants us to figure out what the surface area of this tower is, and it's also telling us that the bottom face of each cube lies completely on top of the cube below it. So basically, that shouldn't be counted in our surface area because it's part of the tower. It's not on the outside, so it's not part of the surface area. So one way we can solve this is to figure out all the surface areas of the cubes individually as if there were no overlapping regions, and then minus the overlapping regions from that total volume. From that total surface area. And then we'll have counted the actual surface area of the tower because, you're counting the surface area of all the cubes and then minusing the ones that you don't want. And that'll give you the total surface area of the tower. So, again, we're going to find the total surface areas of the cubes individually as if they weren't overlapping, and then we'll minus the overlapping regions. So what will this be? The surface area of a cube with side length n is just going to be 6n squared, because a cube has six faces of squares, and those squares are going to have the same side length, and so each of those squares is going to have an area of n squared, and there's 6 of those, so the total surface area of that cube is going to be 6n squared. So for each of these cubes, the surface area is going to be 6 times 1 squared, 6 times 2 squared, and so on to 6 times 7 squared, and we want to add all of those up. So I'll write it right here, 6 times 1 squared plus 6 times 2 squared plus dot dot dot, plus 6 times 7 squared. And here, you can factor out at 6, so it'll be a little bit easier to solve, like a little bit faster to solve. Like, on the AMC, you're not going to have a calculator, so you might want to make the like raw adding, subtracting, multiplying, dividing math a little bit easier for yourself, so it's less likely to make mistakes, and it's also faster for you. So I'm going to factor out the 6. And now here, here's a pretty simple equation. You could just add all of these individually, but there's actually a pretty nice formula that gives you the sum of integer squares up to some number, and it's pretty fast. So I'll use it to find what the sum of this is, but on the test, you can just add these up. It's not too much slower than what the equation does, and it's totally fine to add this up. It's not going to take much time, but I'll just show you the formula. So if you have a sum of integer squares starting from 1, so 1 squared plus 2 squared plus dot 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 plus to some n squared, there's a formula that says this is equal to n times n plus 1 times 2n plus 1 over 6. So with this formula, we can find this sum pretty fast. So in this case, our n is going to be 7. So then this sum will be 7 times 8 times 15 over 6. And we're multiplying it by 6 anyway, so let's just cancel out these 6's. So this sum is going to be equal to 7 times 8 times 15. And if you work that out, you'll get 840. So if we sum the surface areas of all the cubes individually, without considering the overlapping areas at all, we'll get a surface area of 840. And now, to find the actual surface area of the tower, we're going to have to subtract all the overlapping regions. So I'm going to go ahead and erase all this, and write 840. So now we just have to figure out what the overlapping areas are and subtract it from 840. So each of these overlapping regions, it's going to be a square that is a face of the cube above it, because the cube above it is smaller. So the entirety of the smaller cube's face will be on the larger cube's face. So if you look at it from a bird's eye view, kind of, but like a cross section of it, there's going to be a square of side length 6 that is being overlapped right here. And same thing right here. This is going to be a this is going to be a square with a side length of 5 being overlapped here. And this is, sorry, my diagram looks kind of wonky, but so this is the 5 cube, this is the 6 cube, and this is the 7 cube. Sorry for that. Maybe I should just write the side lengths in the center so it doesn't look so you can't get confused, because like if you write it on the sides here, you might get confused which one's which. But I'll write the side lengths in the middle. So right here, this is going to be an overlap region of a square with side length 6, square with side length 5, and so on, all the way to square with side length 1. And this bottom face is not being overlapped because in the problem it tells you that except for the bottom cube, the bottom face of each cube lies completely on top of the cube below it. So it's basically telling you that this side isn't overlapping with anything. It's just like floating, I guess. So count that bottom area. So don't subtract it. So basically we just have to subtract all of these squares, square of side length 1 all the way to square of side length 6 from 840. So let's do that. So what it's going to look like is something like this. So this each of these squares is going to have an area of n squared. So we're going to have to subtract 1 squared, subtract 2 squared, subtract all the way to subtract 6 squared. Now, this is actually the wrong answer to the problem, and I'll tell you why. So whenever we minus these overlapping areas, we actually have to subtract them twice. Now, why we have to subtract them twice is because how we originally counted our total surface area was we counted the total surface area of all the cubes individually as if they're not overlapping, right? So this area right here that's being overlapped, when we counted it individually, we counted it as part of the 7 cube, and we counted it as part of the 6 cube. So basically, we counted it twice. But we want to count it 0 times, right? We don't want to count it at all in our final total surface area. So because we counted it twice, but we only want to count it once, you have to subtract twice of all of this. So here, I'll be ready. So you have to subtract twice of all of it, 1 squared plus 2 squared plus ... plus 6 squared. I hope that makes sense. If that doesn't make sense, let me know in the comments below, and we'll try to answer your question. But anyway, let's just move on. So this is the actual formula for the surface area of our tower. And, again, you can just, solve this regularly by adding it. But, again, I'll show you the formula way. So we can use the same formula as last time, with n being 6 this time. So then this sum right here is going to be 6 times 6 plus 1, 7, times 6 times 2, 12, plus 1, 13, over 6. So those are going to cancel, and that's going to be 91. So now we have 840 minus 2 times 91. And that's going to give you 658 as your final area. And that is going to be answer choice B. So now let's go on to number 8. What is the median of the following list of 4,040 numbers? 1, 2, 3, ... to 2020, then 1 squared, 2 squared, 3 squared, ... to 2020 squared. Alright, so we have a sequence of 40 numbers, and we have to find the median of that sequence. And so half of the sequence is just the natural numbers from 1 to 2020, and the other half of the sequence is the natural number squared from 1 to 2020 as well. Now, obviously, the list that they give us is not in least to greatest order yet, right? 1 squared is obviously less than 2020. So basically, we have to kind of arrange it from least to greatest ourselves, but not actually do it to all of the numbers, because that will take too long. We just want to find what the median is. So 40 is an even number, right? So when you have an even numbered list, like a list with an even number of things, the median is going to be in between two numbers, and it's going to be the average of those middlemost two numbers. So what we have to do in this problem is we have to find the middlemost two numbers, which is the 2020th number and the 2021st number, and then average those two, and that will be our median. So again, we have to find what the 2020th number is and the 2021st number is, because those are our middlemost two numbers, and then average them, and that will be our median. So how I would solve this problem is, I know generally the natural numbers are much smaller than the natural numbers squared, which means that most of the natural numbers will build my first half of the sequence. So the first half of my 40/40 numbers will be mostly natural numbers, will be mostly 1, 2, 3, all the way to 2020. But there will be some insertions of the squares into the sequence, right? Like you would have to add 1 squared in there, 2 squared like in there, and so on, right? But you only add a few squares into there. So I'll consider this as, like most of my first half of the sequence, right? So let's consider we're not adding any squares yet. Let's consider we just have the natural numbers as their first half of the sequence. If this is just the first half of our sequence, then our 2020th number will be 2020. But if we add in more numbers, so if I add in like, let's say, I don't know, just add in the 0 there. I'm counting an extra number here so that this 2020th number place will have to shift down 1. So then our 2020th number will be 2019 actually. So basically, every number that we add in, it will shift our 2020th number down by 1 place, right? So if we count how many squares that we had to add in, that's the number of places that our 2020 number will have to shift down. And it only shifts down of increments of 1, right? So then we can just solve that to find what our 2020 number is, right? And then our 2021st number is going to be the number that's just 1 above that. And then, we would have found both numbers, and then we could get our answer. So let's go ahead and do that. So we have to find which squares we can insert into this sequence. So you want to find the largest square that is less than 2020, but is greater than, you have to find the largest square that is less than 2020. You have to find the largest square that is less than 2020, and all the squares under that will fit into the sequence, and all the squares over that will not fit into the sequence. So 44 squared is 1936, and 45 squared is 2025. I just did this right now, with a calculator, but like on the actual test, how you could deduce this is just from, like 40, you know pretty quickly 40 squared is 1,600, and pretty quickly 50 squared is 2,500. You want to find the square that goes right up to 2020, and because these two squares are pretty like 2020 is pretty in the middle between these two squares, you can test the middlemost squares like 44, 45, 46, and see which one is the largest without going over 2020. And so you'll see that 44 squared is 1936, 45 squared is 2025, which means that 1 squared, 2 squared, all the way to 44 squared will be inserted into here. And all the numbers after that will not be inserted in there. So in total, we're inserting 44 numbers into this sequence. So if we're inserting 44 numbers into the sequence, that means our 2020th number place will be shifted down 44. So instead of being 2020, it'll be 2020 minus 44 for our 2020th number, because we're shifting it down 44 places, and because this is a list of natural numbers. Each time we shift it down 1 place, we're subtracting 1 from our number, right? And it doesn't conflict with any of the squares because 44 squared is 1936, right? But 2020 minus 44, that's just 1976. So this doesn't reach 1936 yet. So it's not going to conflict with any of the squares. Like, if we had a higher like square that was in here, if we were at 2030 instead, if our sequence was the natural numbers, so 1 to 2030 instead, we would have to put in 25 squared, which is 2025, into that sequence. And when we put it, oh, it's not 25 squared, sorry, 45 squared. So we had to put 45 squared into our sequence, which is 2025. And this number is really close to our maximum. So whenever we shift this number down, we have to be careful because we can't subtract 1 every time. Because we're going to have a duplicate, we're going to have two 2025s in the sequence, right? And when we shift that down a place, we're actually not subtracting by 1 because we added that duplicate square number into there. But because here our square is small enough, right? It's 1936. Right now we're just having at 1976, way higher than 1936. We're not going to conflict with the squares at all, which means we can just minus 1 for every of the places that we're moving it to the left of. I hope that explanation makes sense. Again, if it doesn't, you can comment below and we'll try to answer your question. So what I'm getting at is that 1976 is going to be our 2020 number. And our 2021st number is just going to be this number plus 1, 1977. And so our median is going to be the average of these, that's just 1976.5. So our answer to this problem is C, 1976.5. Alright, let's move on to number 9. How many solutions does the equation tangent 2x equals cosine x over 2 have on the interval 0 to 2 pi? Alright, so looking at this, it's a pretty hard function to solve arithmetically, right? We have trigonometric functions. So, an easier way to solve this problem is to actually graph the functions. And we can do this because all it's asking is how many solutions does that equation have, right? If it's just asking how many solutions does it have, we don't have to find actually numerically what those solutions are. And so with a graph, with just a wonky estimate graph, you can still find the number of intersections that those two graphs have and find the number of solutions that they have without having to solve it numerically, which would take a much longer time. So what we're going to have to do is we're going to have to graph tangent of 2x and cosine of x over 2 on the same graph and count the number of the intersections on the interval 0 to 2 pi. And let's just try graphing them individually first, and then we'll combine the graphs. The first function that we have to graph is tangent of 2x, and my expose doesn't seem to be working well here. We have to graph tangent of 2x. So this is just a version of the parent function tangent of x, right? It's just a horizontal compression of 2 of tangent of x. So I'll go ahead, I'll graph tangent of x first. The parent function of tangent of 2x, and then I'll shift tangent of x so that it is tangent of 2x, and then we'll use that graph for tangent of 2x. So here's what tangent of x looks like. Here's y equals 0. This is my y-axis. This is my x-axis. And we're only graphing 0 to 2 pi. So here's 2 pi. Here's pi. Here's 3 pi over 2. And here's pi over 2. So tangent of x starts at x equals 0, y equals 0. It starts at the origin. And then it goes to an asymptote all the way up at pi over 2. And then it comes down from the asymptote from pi over 2, and it goes to 0 at pi. And then it goes up 3 pi over 2, and there's an asymptote right there. And we come down from the asymptote, and we hit 0 at 2 pi again. So you should have your general trig functions already memorized, like what they look like. But if you don't, you can also just figure out these values, like generally what this looks like from tangent of x equaling sine of x over cosine of x. right? So at these asymptotes, cosine of x equals 0. So you're dividing by 0, you're going to have an undefined value, which means you're going to have an asymptote on each of these values, which cosine of x equals 0 at. And the values of which sine of x has a 0 at, the tangent of x will also equal 0, and so these points are where sine of x equals 0. So even if you just need that, you can get a general look on how tangent of x looks like. But again, I would advise you to just memorize the general trig functions and what they look like. So tangent of 2x is going to be a horizontal compression of 2 of tangent of x. So basically, we're going to shift all of the x values like down by 2, by a factor of 2. So here's 2 pi, here's pi, here's pi over 2, here's 3 pi over 2. So before we had an asymptote at pi over 2, now it's going to be compressed to pi over 4. So here's where our asymptote is going to be. I'm not going to draw the asymptote, but I'll put the line going infinitely up there and coming from infinitely down here. And so this is 0 at pi. It's going to be compressed to pi over 2. So there's going to be a 0 at pi over 2. And this is just going to repeat itself. We're going to have an asymptote right here and 0 at pi. So here is what a graph of tangent of 2x looks like. Alright, and now let's try graphing cosine of x over 2, and then just combine the graphs together and find the number of intersections. So again, I'll graph the parent function cosine of x, and then I'll use the transformation. So again, we're just graphing on the interval from 0 to 2 pi. And I'll put this as 1 and this as negative 1. So cosine of x is going to start at 1 at x equals 0. It's going to go down to 0 at pi over 2. And it's going to hit negative 1 at pi. And it's going to go to 0, back up to 0 at 3 pi over 2. And then it's going to hit at 1 at 2 pi. So here's the whole wavelength of the function. It's of length 2 pi. And so cosine of x over 2, I'm kind of running out of space. I'll put it up here. I'll erase this because we don't need it anymore. Cosine of x over 2 is going to be a transformation of cosine of x stretched by 2 horizontally. So graphing takes pretty long. On the actual exam, you shouldn't be like labeling all of these points like I am. I'm just doing it for clarity of what I'm doing. But like on the test, you can just draw these tick marks and know that these tick marks mean pi over 2, so that you don't take up a ton of your time. But anyway, this is going to be a horizontal stretch by a factor of 2. So I'm still going to start at 1. The 0 at pi over 2 is going to be at pi. This negative 1 is going to be at 2 pi instead. So it's just going to look like this. So not that interesting. It's almost just like a straight line. So now we're going to combine our two functions together. Tangent of 2x equals cosine of x over 2. We'll graph them together here. Here's cosine of x over 2. And here's tangent 2x, boom. And then boom, and then boom. And then boom, and then boom. Alright, so now we just have to count how many times they intersect. Pretty simple job. You got 1, you got 2, you got 3, 4, and 5. So we count 5 intersections. That means there's 5 solutions to this equation. And after you graph this, you can see that like my graph can be pretty bad, but it would still be like like I would still probably get the answer right, because this is almost like a straight line, and the tangent function goes like straight up at like these amount of times. So sorry, basically what I'm trying to say is that after looking at the functions, you can see that this problem was probably originally designed to be solved by graphing, right? Like what I'm saying is, if we had equation that was like, you had to get like a really you had to like approximate it really well um, in order to find the actual number of intersections that it has. It probably wasn't like designed to be solved that way. Like, if we had a thing that looked like this, like it was a parabola like here, and we had let's just say maybe let's just do a tangent function. So boom, 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 and so maybe like here it was like unclear whether this tangent function will cross this again, or if it was inside this parabola, so that it never crosses this parabola. So whether this line has only one intersection or it has two. So like if our problem was like this, it would be hard to tell with a bad graph, right? So then maybe this problem wasn't designed to actually be solved by graphing. But we can see that this is really easy to tell, even if you had like a terrible, terrible graph. As long as you got the general idea of what the functions look like, you would probably get 5 intersections. So, we were supposed to solve it by graphing, and it was the fastest way. So yeah. So our answer is going to be E5 to number 9. Now let's move on to the last question, number 10. There's a unique positive integer n such that log 2 of log 16 of n equals log 4 of log 4 of n. What is the sum of the digits of n? Don't get tripped up by them asking you what is the sum of the digits of n. That's just another way of them asking you to find what n actually is. If they just asked you to find n, and then they listed the choices of n, people could just plug in those values of n to see which ones work. So when they ask some of the digits of n, you can't plug in those to the equation and see which one works. So when they ask you some of the digits of something, they just want you to find what that something is, unless it was actually like one of those tricky problems where you had to like manipulate it so that you get like the sum of the digits, but whatever. So they just want you to find what n is here. I'll write this equation down first. We have log 2 of log 16 of n equals log 4 of log 4 of n. So one thing we can notice about this equation is that all the bases are powers of 2. So we can utilize this by converting all of these bases to 2. And it's easy to convert because all of these bases are already powers of 2. And we can use a formula that will put it into log base of 2. So, if we have all of them as being log base of 2, we can probably simplify our equation further and find what n is. And remember, we want to isolate n. But right now, there's not really much of a sure way of where to go. Like, if you peel the layers of this n by, raising it to 2, raising it to 16, you're still going to have a stuck n there. Like, what are you going to do about that? So, I think a good way to start with this problem is by converting all of them to log base 2. So, we have a formula of log of a to b. So it's log base of a to the power of b of c is going to equal 1 over b of log base a of c. And so that's what I was talking about, why it's easy to convert these bases to 2, because they're powers of 2. We can just put that 1 over to whatever power they were at, right? So I'm going to go ahead and do that. So 16 is 2 to the power 4. That means it's going to be 1/4 log base 2 of n. And it's going to be 1/2 of log base 2 of 1/2 of log base 2 of n. Alright, a little bit messier, but now we have logs as all base 2's. Now, we can utilize the log property of addition backwards, in that we can put this as, we can separate these two values, 1/4 and log 2 of n, as log 2 of 1/4 plus log 2 of log 2 of n. That's just the log property of addition backwards. If you add two logs with the same bases, it's that same log of the same base of those two things multiplied together. So this would be the opposite of that. We're separating it back into the log plus log. And the reason that we would want to do that is because when we separate it into here, when we separate it into log 2 of 1/4 and log 2 of log 2 of n, we're separating it into constant and we're separating it into variables. So the more you separate the constants from the variables, you're getting closer to solving for the variable. So that's a good thing to do. So I'll go ahead and do that. It's going to be log base of 2 of 1/4 plus log base of 2 of n equals 1/2 of log 2 of 1/2 plus 1/2 of log 2 of n. Oh, whoops. 1/2 of log 2 of log 2 of n. Alright. So again, it looks pretty messy, but we've got these constants here, which are really nice, and we've got these variables here, which are nice. So we've separated the variables and the constants more. So log base 2 of 1/4 is just going to be -2. And log 2 of log 2 of n, you can't simplify that yet. We'll just write it as log 2 of log 2 of n. And then log 2 of 1/2 is going to be -1 times 1/2 is going to be -1/2 plus 1/2 of log 2 of log 2 of n. Now look here. Look what's really, really nice here. The parts with our variables, log 2 of log 2 of n and 1/2 of log 2 of log 2 of n, they're in the same form. We can combine these two together, right? They both have log 2 of log 2 of n in them. Like, if we treated log 2 of log 2 of n as x, then you have x and 1/2 of x. You can combine those together. And that's really good because you're combining your variables into one term. So when you have your variables into one term, you're basically done already. Then you just have to remove the layers, and then you'll get your answer. So this is really good. And we'll move our constants all to one side. Let's move all our constants to this side, and move all our variables to this side. So if we have log 2 of log 2 of n minus 1/2 of log 2 of log 2 of n, that's going to be 1/2 of log 2 of log 2 of n. And then putting -2 over here, that's going to be 3/2 here. So again, like I said, this is really nice. Now we just have one instance of our variable, peel back the layers, and we'll get our answers. So we see the light at the end of the tunnel now. I'll erase this for some more room. So first multiply by 2 on both sides. We have log 2 of log 2 of n equals 3. And then we're going to raise both sides to the power 2 to get rid of the log base 2. So then we have log base 2 of n equals 2 to the power 3, or 8. And then raise both sides to the power 2 again to get rid of this. Then we just have n equals 2 to the power 8, which is going to equal 256. So there we go. We got our answer 256. And it wants us to find the sum of the digits of n, which is just going to be 13. And that's going to be our answer E. Sorry, I came back and erased the board, but I wanted to discuss another way of solving this problem. So I'll write the equation down again. So it asks us what is the sum of the digits of n? So when it asks us that, it's pretty safe to assume that it is going to be an integer, right? Certainly, if n was a fraction, you cannot say find the sum of the digits of n. And if n was a decimal, you would generally not ask that either. Because you could also like put that decimal into a fraction, and people would get confused, like why are they asking for some of the digits of a fraction? So it is pretty safe to assume that n is going to be an integer. Now, this way is just it's kind of like a clever faster way to do this. It's just by noticing a thing that will speed up your problem solving process a lot. So what it is you assume that log 16 of n will be an integer. Okay, so it's likely that because n is going to be an integer, all of this is going to like work out really nicely and give you maybe like integer equals integer. Okay, so we can start by log 16 of n being an integer, and if that doesn't work, we can try lower powers of lower bases of log and seeing if that works. But what I'm saying is, sorry, n is going to have to be at least a power of 2, right? Or else then it'd work out like really weird. We start out by assuming that n is a power of 16. Okay. And if this doesn't work, we can put it to lower powers of 2. But eventually this should work, and it should work pretty fast because n has got to be a power of 2, right? So we'll just start by assuming n is a power of 16 because there's a log base 16 here. If n was a power of 16, it would work out with this log base of 16 really well. So maybe we should just try some powers of 16. So the first power of 16 is going to be 1, second power of 16 is going to be 16, and next is going to be 256. Let's just start by testing those. So log base 16 of 1 is going to be 0. But you can see that this already doesn't work. You can have log of 0. So let's test 16. If you have log base 16 of 16, that's 1. So then you have log 2 of 1 equals log 4 of log 4 of 16. Log 4 of 16 is just 2. And then this is going to equal 0, and this is going to equal 1/2. Sorry. And so, but 0 does not equal 1/2, right? So that means 16 is not going to work. And then we can try 256. 256, log base 16 of 256 is going to be 2. So log 2 equals log 4. So 256 is 16 squared. So that means it's going to be log 4 of 16 squared, or 2 times a log 4 of 16, or 2 times 2, or 4. And here we have log 2, which is 1, and log 4, which is 1. So we have 1 equal 1. We have equality so that we see n equals 256. And this is just a way to solve it faster. On the test, you might want to consider doing it this way because time is very valuable on the test. And if this method wasn't working, you can try by reducing this power, like 8 to the x, 4 to the x, and so on. Or maybe just saying n equals 2 to the x, and putting it through all of that, and solving for x. And then when you solve for x, you also solve for n. But that's going to be it for today, guys. I hope you enjoyed the video. If you have any questions, make sure to leave it in the comments, and we'll try to answer them to the best of our power. Yeah, thanks for watching. Bye.